Good morning, everyone. We are just waiting for Dr. Debris to join the session. Then we will start the session. Hello, everyone. Welcome to the first day of lecture series on downscaling of climate data and different climate models for analysis. We have Dr. A.P. Dimri with us, who is professor in the School of Environmental Science, Jawaharlal Nehru University, New Delhi. So we welcome you, sir, and we request you to please start the session.
Thank you very much. I hope I am audible to all. Good morning.
Yes, sir.
Good morning. Thank you for interacting with so many people, and I assume that most of you kind of understand climate model and dynamics scaling. Of course, the climate change in the present context is very hyped case in that context, and by virtue of this hype, of course, there are various dimensions which are linked to various facets of scientific domains, be it agriculture, be it uh, water, be it plant. So everywhere it has come, and that is the case where the reason of understanding of climate has come. Well, modeling, when we are talking, let me tell you, it's a kind of in a with a set of equations. We are trying to simulate a atmosphere or nature, not only in climate in that sense, even the plant dynamics, even in the mathematical formulation, in the physical processes. We are trying to simulate the nature based on certain equations. In my case, it's a conservation of mass, momentum, and energy. As we know these cases, these laws in our earlier classes, and then how mathematically these processes are formulated in the classes. So these are the basic fundamental principles based on which we try to kind of. Is there some noise coming in between? I'm sorry. It's not from my side, I hope. So we are trying to simulate the nature based on the equation. Why? Because we want to see how the climate will be in the future and how the climate will be in the past if we are doing geological modeling and if we are doing climate. Because present we have observation of data for hundred of years as far as the climate is concerned, and we want to see based on these 100 years of data what's going to happen in the future and what's going to happen in the past. So many of you, if you are from geology background, you must be knowing the proxy data based on steering, speleothem, and so forth. So we try to understand the climate based on these factors, based on these equations, based on various methods, and we say that at so and so time, what is the climate at so and so place. So when I said time and place, I'm talking on space and time dimension. Space, we talk lat, long, and vertical, latitude, longitude, and z, and temperature, and t is the time. It means that with time, things are changing. And as we know, Earth-Sun system, basic radiative forcing in the Earth-Sun in Earth comes from Earth-Sun system, and there is a kind of processes which work, the processes which deal to redistribute this energy. I am not going to the radiative transfer processes right now, but I'm just some flip of the process which kind of understand these intricate complexities within the physical processes happening in the free atmosphere, and then we talk of the climate, right? So these are the fundamental few of the preamble I wanted to share with all of you, that how climate looks like, and if that is the case, then how we can interpret various factors and various processes associated with this. And that's where we kind of understand that this is the climate happening. If with this we start, most probably I will like to add upon that I chose today's talk climate over the Himalayas. First, for any process we need to understand what we want to know. And I'm told that it's a very heterogeneous class. Many of you must not be from climate background or mathematical physics background, so I'll keep my discussion at that level. However, at last, if anybody has any kind of query, clarification, or doubt, or any suggestion for me, please feel free to note it down right now. The 5 minutes before my leaving at, and then I'll be happy to interact on this today. Then I'll go in a bit more critical mode ahead. So what is the climate when we are trying to understand on the sense? I hope all of you can see my computer, my screen in the computer, and most probably we'll go one by one with this discourse of the computer. And if you are interested, you can please follow this with the organizers. I'll pass this presentation to them, and based on this presentation, if anybody, so I deliberately chose to speak climate over Himalaya because Himalaya is a very complex subsystem within the earth, where in itself there are various processes working at tandem together. There is a plant life, there is a animal life, there is a glaciers, cryosphere, there is a water, there is a rivers coming down, and various habitat around this Himalaya. Not only India, surrounding total 8 nations are dependent on this river drainage, river hydrology. There are disasters. A few months back, we heard of Chamoli disaster, cloudburst, floods, landslides, avalanche, rock failure. So there are plenty of physical processes that are happening within a subset of within the subset of Himalaya. Now, when I say Himalaya, our understanding of Himalaya in general is particularly from the context of geological massif protruding out of the region, and that is primarily on geological processes. The basic fundamental understanding how Himalayan orogeny has come, people say that because of the tectonic Tibetan plate and Asian plate and Indian plate, when they came in front of each other, they collided, and then Himalayan orogeny started becoming the 50 million years back. So this is the tectonic mountain have started building up because of the push, and then there is a crack and all those fault failure and all those come. I'm not geologist, so maybe some geologist can explain this much better than me. In second case, when this Himalaya started protruding outside the earth 50 million years back, it stopped after some time when it's grown enough that it stopped northward propagating air, and that's what become Indian summer monsoon. In the summertime, you have a lot of rain, all of you must be. And when the rain started coming 15 million years ago, recently there is some study based on the benthic proxies. They say the Indian summer monsoon was 22 million years back. But in general, what as of now I know, it's a 50 million years back the Indian summer monsoon started coming. And when it started coming, it's imprinting on the Himalaya continuously, this raindrops, and hence there is a weathering started taking place. And the Aravalli, the Sivaliks in front of Himalaya is not tectonic mountain, it's a sedimentation mountain. So all the eroding material, sedimentation which occurred on this due to the monsoon interaction had made a frontal Sivalik mountain. So there is a lot of confusion people have. Sivalik is non-tectonic mountain, it's a sediment mountain which has come. Anyway, so it becomes a very complex subsystem within the Himalaya. So geologically we consider it like that, but if you go slightly deeper from different subjective sides, we have a very beautiful working experimental lab in Himalaya. It starts from climate, it starts from various topography, and then there is a lot of water tower, people call it, in this third pole, people call it. Some in Indian mythology, it's revered as a home of the Lord Shiva. So there are various manifestations. This Himalaya, if you are thinking beyond the geology, have come into the context of social, scientific, and activism life. You have a various religious pilgrimage. So this is the one of the, I'll limit to only the climate discourse. I will not go in many discourses of the subjective downline, but rather I'll be confining myself to having the climate discourse. And then we can say that outside the polar region, it has the longest glacier also. So you have a glacier mass, you have a mountain chain, youngest mountain chain, you have water frozen within that in the form of permafrost, in the form of snow, in the form of glacier, so and so forth. And more than 1.5 billion people's life depends on the river originating around it. Our Ganges, Yamuna, Brahmaputra, other side you have Amu, Darya, you have a lot of rivers going to the Indus River Basin sustaining the Pakistan, Afghanistan. So plenty of rivers are kind of exiting from this eastward moving, northward moving, and so they supply a lot of water into the surrounding nation and helps the sustaining the habitat across this. It's a very heterogeneous, as I rightly said in the beginning, that the evaluation or origin of Himalaya brought very heterogeneous evolution of rock mass. It's a unique topography changed. We have a topography from 1000 meter to roughly 7000 meters in general. We have land use, land cover which changes. We have a snow line, we have vegetation line, and then there are natural processes and there are man-made processes also. Man-made processes could be like cutting of the trees, cutting of the roads, hydropower projects, and so on and so forth, religious things and so on and so forth. So several studies have talked of the climate changes over the Himalaya, and when you see Himalaya from the climate point of view, we must see that Himalaya is not a homogeneous climatic subzone. Northern, Western Himalaya and Central Himalaya and Eastern Himalaya, they have very different regional perspective, very different regional perspective. In that context, if we are talking of the regional perspective, we say that temperature of the region is increasing somewhere differently, other where not in the similar manner. Somewhere precipitation is increasing differently, somewhere in a different manner. And second thing, then you also have elevation dependent warming. Elevation dependent warming, what I mean to say here is that as you are climbing up in the mountain, the elevation decreases, temperature is decreases because of the lapse rate. I'll not go in those details. When you climb up, the temperature decreases, all of us know. However, when we are talking of the trend of warming in the past years, we find that higher elevation have more warming rate than the lower elevation. So in due course of this, what's going to happen? If higher warming rate is happening in the upper region than the lower region, you have more dry atmosphere will be available here, because temperature comparatively the past previous will be increasing in higher Himalayas more than the lower Himalayas. And hence, what is going to happen? The vertical change on the gradient in temperature will also play altitudinal response to determine the precipitation, moisture, and temperature feedback in manifesting the various impacts on tree line, vegetation line, or maybe the wild animals' existence, which we are seeing the conflict. So in case of temperature, in case of precipitation, it shows a very complex picture. Why complex picture? Because it's very difficult to determine its sign, magnitude, and significance of change in time, along with various varying regional responses, because responses from the surface fluxes to the existing adjacent atmosphere is not similar or across the Himalaya right from west to east. So the responses to these varying signals are also very different, and it's very difficult to say how precipitation is changing over the whole Himalaya. However, in general, we can say there is a kind of more precipitation is kind of trying to pull at the surface as compared to the higher Himalayas. I'll show you the results. In fact, few results based on which you can comprehend it much better in that context. Available information of the Himalayan region is quite scattered. We don't have data. Now you don't have observation, you have a less information available. So work becomes itself difficult to kind of justify what you are telling over the Himalayan region, and then your focus of different section of the Himalaya rather than adopting a holistic Himalaya becomes a very key. So somewhere you have a good number of observations. It doesn't mean that this region of the Himalaya will be dictating whole Himalayas. That's not the case. It's very deceptive otherwise. So what's that then? Many researchers, many projects are working in such a manner that they are very good in one kind of region, but not the other kind of region, like that. And then hence the single study needs a kind of underline, and most multimodal study is needed. So these few things I have shared, in which I'll be deliberating on my present class based on the modeling philosophy and how good and how bad the models are, what's a good thing in model, what's a bad thing in the model. But we must understand this philosophy of regional climate model. Basically, What we are trying to say, that model is a kind of a simple tool where we are generating some kind of a number, some kind of processes, which otherwise is not possible because of the paucity of data. If there is a paucity of data, we may not be able to generate these kind of a context. So based on this, most probably we will be talking in the model, because model will represent what we do not know, but with certain error, certain deviation, certain uncertainty. So we have to look into this aspect, that if I can simulate the good numerical model over this region, and then I look with certain kind of validation, wherever we have observation in the valley, wherever we have observation in the basins, wherever we have appropriate processes represented or not in this regional climate model. Based on this benchmarking and uncertainty of the model, we try to determine how good and bad is our mathematical models, and with based with this character or good and bad, we try to move ahead in the process, and based on that, then we talk about this. So this is the Himalaya I am representing. If you see from cross-sectional view of this Himalaya, we find that the elevations are running from Shivalik 500 meter to higher Himalaya till 6,000 meters. So it's a very complex, and simultaneously, if you look at very carefully, we have a lot of valley, lot of ridges, lot of subsurface changes are there. They are not uniform. So why it is that we want to talk? Because this feature is also interacting with the adjacent atmosphere on top of it. So there is a coupling of the atmosphere as well as the fluxes which are exiting or going into the Himalaya is also working. So that's very important to know the physiography of the Himalaya, based on which we try to determine what kind of fluxes will be determined based on the Himalayan complexity, and how these complexities can be resolved up to certain extent, whatever the understanding we have based on the processes known and based on the modeling framework, and then we go ahead with a good and bad uncertainty. So this is the Himalaya. If you are talking now, when I say uncertainty, it means that there is something hidden we do not know. And how we can remove that uncertainty, or how we can minimize that uncertainty. What do I mean by that? The observation what we have, the climatic uncertainty, if you are talking in this first panel, if you are talking, we see that they are the gridded precipitation averaged over 30 years time. Now, all these three gridded observations from Aphrodite, GPCC, and CRU, right? They all three show very different sub-regional kind of distribution. They are not same, right? In a larger look, they give a almost clear distribution of precipitation, that it should be like similar. But if you minutely look at northeast, lower Himalaya, and higher Himalaya, you have a different kind of distribution of precipitation is happening over this region, right? And if you go down and if you look at the precipitation climatology and its altitudinal uncertainty with the blue dot with different elevation change, we find at the lower elevation we have, is my figures visible to all of you?
Yes, sir.
You can see it well, right?
Yes, sir. Yes, sir.
Okay, thank you very much. So in lower Himalayas, when you see that your blue scattered dot are spread more, but as you climb up in the higher atmosphere, they are scattered closely. And that's what gives a very unique distribution of physical processes, that millimeter intensity of precipitation millimeter per day is more variable in the lower Himalayas. But as we climb up in the higher Himalaya, they have less amount of variability as compared to the lower Himalaya. It means that it indicates to the physical processes where precipitation forming mechanism, as the moisture climbs up, start climbing for the lower hill, is having more kind of interaction occurring for the precipitation forming mechanism. And that's where we find that a lot of variability is existing. Once the process started climbing up in the elevations, we find that comparatively the precipitation mechanism is less variable, and most probably it will be less intricate, less complex also, because very first interaction of moisture is taking place at the very lower Himalayas and foothill of the Himalayas. Second, precipitation trend, if you look at that, we find very distinctly it will climb from lower Himalaya to higher Himalayas. In lower Himalayas, our precipitation trend is shows in last 30 years the precipitation is decreasing, right? But precipitation, as we climb up to the mid Himalayas, precipitation trend seems to still be negative, still decreasing. But as we cross the threshold of 3,000 meters, we find that precipitation is increasing, though very small, but it's increasing above mid 3,000 meters and above. What does it mean? It means that in last 30 years time, the precipitation forming mechanism, which must be governed by certain energetics, which must be driven by certain physical processes leading to the manifestation of precipitation. It shows that precipitation is decreasing in the lower Himalayas, but as we climb 3,000 meters and above, precipitation seems to be increasing. It means that the threshold of precipitation forming mechanism is slightly maybe moving to the higher Himalayas. We have to talk on that. Coming to the temperature also, we find that temperature again in the all regarded observation doesn't show the similar picture. All are based on certain kind of observation. I am not going into those detail of data analysis and data methods of this data analytics. We however see here that the temperature distribution in all the seasons, December, January, February, March, April, May, June, July, August, September, and October, November. 4 seasons I have chosen the vertical column, and in row there are 5 graded observation I chose from Afrotemp 0.5, 0.25, crew, UNW. So what I mean to share with you people is that all the regraded observation itself has the difference in the method and formulation of the data. The observation itself has kind of uncertainty. Now, if you ask me which observation, regraded observation should you take, maybe I will not be able to answer it until and unless I don't look at the method, which method has generated best data based on their statistical method. Because input data, input source are similar, but the statistical method are different based on the statistical method. Then you have difference in the distribution, spatial distribution of data which is happening. And of course, if you look at the blue scatter plot, as we climb up in the free atmosphere, we have a decrease in the temperature going up from lower elevation to higher elevation. Of course, it is a dry adiabatic lapse rate or saturated adiabatic lapse rate. I am not going on those physical process detail of the atmosphere. However, I would like to say that in atmospheric, vertical atmosphere, lapse rate doesn't work in the Himalayan region, in the mountain region rather, I would say, because you have a valley which interact with the energy, which is doesn't leave the vertical atmospheric lapse rate functional or applicable in the mountainous region, because there is interaction of heat which is occurring from the valley walls, which is not the case in the free atmosphere otherwise. So we have to keep that aside, but keep in mind that in atmosphere in Himalaya, free atmospheric lapse rate doesn't work. So all of you must be knowing the Codex South Asian experiment. It is done based on to improve upon the model strategy. Here I am showing few results based on the model which I have chosen. There are plenty of model now till today. Now Codex South Asia is very overused experiment. Many people have used it, and next experiment of Codex Core has come into the existence. Now, if you look at in these lines, you will find I am writing at one place 0.44 resolution, which is roughly 50. What does that resolution mean here? It means that the resolution of one grid simulation, if you look at this picture, is 50 kilometer by 50 kilometer. It means that model will give at 50 kilometer by 50 kilometer one temperature value. Now over the Himalayan region, 2,500 square kilometer, you get only one value, or 15 to 50 kilometer. So that's grid spacing we have. But in Himalaya, that is not very successful in the sense that you need much finer detail. So we need to go to the finer resolution itself. Either you host has discussed about the downscaling. So we'll talk on the downscaling and bias correction tomorrow. So this grid spacing is good for heterogeneous land, but this grid spacing is not that suitable for the Himalayan region. And now we'll get to that, why and what not it is suitable for the Himalayan region. So if you look at these cycles here, the monthly cycle, if you look January, February, March, I used almost 11 ensemble members in this and compared this mean cycle with the corresponding observation. I chose Aphrodite, and based on that I have compared this with Aphrodite. We find that annual cycle has a peak. Of course, that peak corresponds to the Indian summer monsoon rainfall. This is a mean precipitation in different months based on last 30 years data I have chosen, and I averaged these 30 years data. I got a mean monthly precipitation for each month, and simply that I have plotted to look that how the mean precipitation cycle in the model look like. In that case, we find that green color shows the real observation in Aphrodite. Rest all the graphs, line graphs are model results. In this, we see that some of the model are totally outrightly bad. They are not showing the annual cycle of precipitation, but some of them are distinctly showing this annual cycle of the precipitation, monthly annual cycle. But what we find very interestingly, some of the model are peaking exactly as the observation. Of course, there will be wet or drier, but some of the model are peaking a month before, or some are peaking a month after, right? So every model has its own weaknesses and goodness. Why we are running the model? Because we have to talk future. We have to go to Jyotsi to tell about horoscope, right? So these calculations are needed if how good and bad we know the future. So knowing the future, first we want to have a benchmarking and assessment of uncertainty based on the available model. Once we are able to do it, then we'll go to the future, to the market, that our model is this good. If you want to buy, please buy it, or you leave it. So that's what exercise first every one of us has to do, that how good and bad model is, right? So we see that some of the model is peaking the peak, but some of are not doing, and some are doing, they are doing either leading or lagging as compared to their corresponding mean monthly cycle of the Aphrodite observational graded observation. If you look at the only monsoon JJS mean distribution, and if we compare with that spatial distribution, I have plotted a bias here. So bias means observation, model minus observation, and we find again the problem that which I discussed in my previous slide, that lower Himalayas is having more complex process in mechanism, and lower Himalayas we find that there is a dry model precipitation as compared to the corresponding observation shows that model has a dry bias at lower elevation, but as we climb into the higher Himalaya, model precipitates more than the corresponding nature. So this we need to understand that how the precipitation mechanism in the model is kind of simulated, and how good and bad it is, right? We must know that how good and bad it is, because based on that good and bad, we need to go into the future, and then we will talk with this much uncertainty we are doing. And there are also other methods which I'll talk tomorrow, that we call it bias correction. If model is that bad, how can we improve upon the model? Physics new method has come. We do the bias correction, and based on the bias correction, we improve upon our result. So that is what we do here. And based on this temporal distribution of left-hand curve, you see this many graphs are running across, and we find that how wet bias and low dry bias in individual. So some of the model are giving more precipitation when we average over this spatial region, and some are doing the dry. So what there is other way we do, we merge them together. So some models goodness, Some models badness cancels each other, and we get a mean state among these 11 ensemble member. So we are using 11 ensemble member. There can be more model run. It depends on how good and bad your computational capacity is, and based on that computational capacity you can simulate as many model as possible. But sometimes it becomes a limitation because you don't have a good computational methods, a good computational infrastructure, and hence you have to limit to your ensemble members. So you can do it, you simulate many models, and based on many model, if you average their output, most probably you get a closer picture to the, can you hear me?
Yes, sir.
Okay. This authentication failed on JNU network, so I thought I lost myself. So, oh, okay. So you see my slides also?
Yes, sir. It's visible.
Yes, sir.
Fair,
Yes, sir.
fair enough. So
Sir,
so now what happens if altitudinal distribution you see in this context of the model, which I picked up this again same figure of distribution of variability in this, and then in the left hand, right hand panel, I am showing only the biases, how the biases are kind of playing a role. We find that at lower elevation, your model has more bias, but as we keep climbing up, you have a more organized setup of the precipitation forming mechanism as we climb up. It could be for few reasons, like in first, the flow of moisture which is coming from down south start coming in interaction with the upslope side, elasticity and energetics comes into the picture, and based on that you have a kind of a resistance from the orography, and based on this resistance you have a kind of more biases occurring in the lower elevation of the Himalayas, because the first time a flow is hitting the mountain there. Second, also that in the lower Himalaya we have more vegetation than higher Himalayas. So you have more variable land use, land cover in the lower Himalayas. So if any flow is coming over this, more land use, land cover will be interacting with the upper atmospheric flow, and based on the upper atmospheric flow, what's going to happen is that you have precipitation forming mechanism will differ up to certain extent. But as you climb up, more precipitation forming mechanism becomes more organized. And when it is more organized, you have comparatively less dry or wet bias as we climb higher up in the Himalayas. So I'm showing you the cross-sectional average of the wet and dry bias. Further, I hope all of you understand biases. It's a technical term, model, field minus observation. So if I am talking wet and dry bias, it means I am talking of the precipitation field, and in this context I am talking of the precipitation from model minus precipitation from observation. I assume observation is correct here, right? I am not going to the observational analysis. So here I am assuming that my observation is correct, and now I want to see how good and bad model is. So if model is deviating from corresponding observation towards plus side, I will say model is wet, means it is giving more precipitation than observation. And if it is dry, it means model is giving less amount of precipitation than the corresponding observation. Getting more critical of model, we do a lot of mathematical and statistical dissection of this model and corresponding physics also, so we can approach to comparatively better kind of, so we calculate correlations, we calculate spatial correlation, and based on the deviations we do a lot of scalar analysis, and based on that we try to look at the model which is comparatively much closer to the observation. Now here we need to understand one point. Now, what you want to see in the model? Do you want to see the mean precipitation? Do you want to see the extreme precipitation? Because they are different field and characteristic. Like we dress for certain occasion, we don't dress for occasions homogeneously. We dress for occasion. So now the context, if you are looking for the extreme precipitation per day, suppose 200 millimeter per day, I'm not interested in mean, because daily we don't have 200 millimeter per day. But sometime if we have like flood researcher, They will be interested of the high volume of precipitation occurring as far as the meteorological flood is concerned, right? So it depends what kind of processes you are more interested to look in the model, and based on these processes you will find one model is good for your extreme precipitation, but the same model is not good for mean precipitation. It means that the model physics to capture the extreme precipitation is good, but it's not being able to capture the extreme precipitation. So similarly, you have to play with many models, and based on this model, we find that based on the 11 ensemble suite of the model, we find that ICHEC, SMHI, RCA4 comes out to the best performing model for the mean of monsoonal precipitation in case of Indian monsoon, JJAS. And if you look at the frequency distribution, it could kind of capture the probability distribution function of the precipitation over the Indian region. But if you go to the extreme of the precipitation, the lowering of the curve which you see, it is not being able to capture, number one. Number two, if you look at the mean of the graph, it is kind of the Aphrodite, the mean is capturing later, so seasonal mean is coming different than the model. So these are the value we need to correct in our understanding in the physical processes in the model. That's very important. And if you look at the scatter plot, we find that lower intensity event in observation and model are very good. They are falling perfectly fine, lower intensity event. But as we climb up, their variability is increasing. And what I mean to state from that scatter plot is that the higher precipitation events like cloudburst or extremes are not very well captured in models, but lower precipitation. So most probably when we are talking of the higher precipitating event, we need to think something different than the common models, because model is good for lower precipitating events in day-to-day manner. But if someday you have a 200 hectopascal, 200 millimeter per day or more millimeter per day, then it is not being able to in that, and hence there is a considerable uncertainty is found. Yes, please. Okay, so the individual performance model vary naturally. You are basically, I generally say that you are kind of experimenting atmosphere or nature based on certain set of equations. So equation at many times are unable to capture the real atmosphere per se, right? You parameterize the equation per se, and simultaneously at the same time you don't have all the variables to force in the model, because nature is much non-linear complex, right? So if that is happening, then how we are going to move ahead? At least you have certain information than nothing as far as the modeling strategy is concerned. So you have to move ahead with modeling strategy with certain information, but with certain uncertainty, but with certain error, good or bad. You can move ahead that this is the case how it looks beyond in the present, because present we have observation at least. So when we are comparing with the present observation, we get to know how much model is deviating from the corresponding observation. And with this deviation, if we go to the future where we do not have observations future, so but however we can say that in time scale we can integrate these mathematical models in future, and we can say that how this climate and mathematical model can be simulated. So with this we found that still consistent bias is there in time and space, which can be removed from the bias correction techniques. So there is evolution of the model, simultaneously there is evolution of the methods to correct the model biases, right? So it depends on the need of the output what we have, and by virtue of that need we are improving on various methods, potentialities, and excellence of performing much better and better. Coming for temperature, we find that various temperature have again a bias in model. What happens, these lower elevations are warmer and higher elevations are colder in case of model bias, temperature bias. So lower elevations are warmer, higher elevations are colder. And if you remember in the case of precipitation, I said that lower elevation are dry It means there are less precipitation. And here we find a corroboration that when there is a more temperature in the model, it is not letting the available moisture to be condensed as compared to the nature. And that is one of the reasons that your lower elevation has less amount of precipitation happening than the corresponding observation, because temperature in the model physics is not letting the condensation occur for forming the precipitation, because temperature is comparatively warmer than its corresponding observation in the lower Himalayas. As you go higher up, temperature cools down. So temperature is colder in higher Himalayas, cold bias. In lower Himalayas, you have a warm bias. And that's what we have again compared here among the various model strategies. We found that the spatial distribution and seasonal variation of uncertainty in all the ensemble members. If you look at the winter, summer, pre-monsoon and JJS, somewhere you are finding the ensemble shows the lot of standard deviation over this region of Himalaya, but somewhere their standard deviation is very less. So certain pocket you have different standard deviation, certain pocket you have higher deviation, and also there is a seasonality of variation is also occurring. Certain season is showing more standard deviation as compared to the winter and as compared to the post-monsoon, October, November. Annual cycle matches very well. If you look at the curve, it matches well. However, there is a kind of a cold bias. All the models are colder than the actual environment. But I'll be happy to go ahead with this graph because I know how much difference it's happening in between the different graphs, and this difference of bias is very distinctly clear to me. So if that is happening in the monthly mean cycle, I can go ahead with this kind of distribution. And coming to the Gaussian distribution over the region, we find that again you have a skewness on kurtosis. You can see here in those figures, when we compare model with the corresponding observation, we find that somewhere mean is not matching, and somewhere if mean is matching, your spread is not matching, or also the mean is skewed to left and right of the corresponding model physics. So this gives us an understanding then where is the mean, where is the spread of the temperature values are happening in the Gaussian distribution of model and corresponding observation. And with this kind of distribution understanding, we will be able to correct the model field for with the help of observation and bias correction. And similarly, the altitudinal distribution of the blue scatter dot, if you look at that figure in particular, we find that there is a kind of intensification of cold bias happening with height. As we climb up in the atmosphere, or with the model atmosphere, we find with the climbing, your intensification of cold bias is increasing than the corresponding observation. So these are kind of many physical atmospheric physics we need to kind of link with the model physics. It's not similarly simple simulating the model. It's not the case. You have to have a kind of a understanding of physics also, processes also. Which process do you want to model? Until unless you don't have a good understanding of the model, good understanding of the process, physical process, it will be very difficult to interpret any of the model fields until and unless you have a kind of basic process understanding what you want to look at the physical process of the model, and then you will go for the future. So far I have discussed on the present. At the present, I have kind of dissected my model, goodness or badness, and based on this present 1970 to 2005, almost 35 years comparative analysis on the climate scale. Now, with this goodness and badness, now I am going with the climate change over the Himalayan region, and that's what I am telling what's going to happen in the future projection, in the near future or far future, and so on and so forth. So if you look at the first panel of the monsoonal mean precipitation, JJAS, mean precipitation over the Himalaya, you can look at the green and brown shades over the Himalayas. Green shade says that the percentage change corresponds to increase in 2020 till 2049 average. That's near future. 2020 to 2049 average shows that precipitation over the greener region is increasing, but precipitation over the brownish region is decreasing. It means that it shows that in coming time, your precipitation which is not be able to go to the northeastern region, by this is shown by various model, and simultaneously some of the model are showing that lower Himalayas and western Himalayas are showing the higher Himalayas. And last panel, right hand corner panel in this 11 ensemble mean, not 11, 1, 2, 3, 4, 5, 6 to 8 at ensemble means. When I average these 8 ensemble mean, it indicates that northeast Himalaya will be deficit of monsoonal precipitation, whereas northwestern Himalaya will be having excess of precipitation in near future. It's a percentage change. So this is what we can see based on our model, goodness and badness in the future. And interestingly, if you look the elevation dependent changes in the precipitation, again, as we discussed that lower in elevations show increased variability in future and higher precipitation in RCP 2.6, RCP 4.5 and RCP 8.5. I used all the 3 RCPs, and based on these RCPs, we are kind of determining if we climb up in the Himalaya, what's going to happen to the precipitation in the future, right? And based on these experiment of dependent changes in from present, we find that features gets more prominent in the most pessimistic RCP. RCPs are representative concentration pathways, and 8.5 corresponds to 850 watt per meter square. It means that if all the humanities do excessive emission, unlimited emission, what's going to happen to the radiation budget? So I'm not going in this RCP 8. I know all of you must be knowing this 2.6, 4.5 and 8.5. So the first panel shows the near future and second panel shows the far future. It means far future is 2070 till 2099, okay, 30 years average, whereas the first above panel is showing the 2020 to 2049. So in the extreme RCP 8.5, uncertainty is also increasing, right, from lower elevation to higher elevation, whereas in RCP 2.6, it's happening less uncertainty. Based on this, we can say that there is a kind of increased precipitation and associated variability is in the future. But this associated variability has very high uncertainty. Coming to the temperature, all of you know most probably that everywhere this debate is going on that temperature is likely to increase, and here also we see that all the 4 season, winter, pre-monsoon, monsoon and October, November is showing a very distinct increase in temperature happening in all the model. So projection is that there is a kind of a, with certain error, with uncertainty, this is the spatially average temperature is happening with certain higher rate of warming at higher elevation is happening. Is it okay?
Yes, sir. It's okay.
Your presentation is not visible.
Suddenly it dropped. I don't know why. Yeah. So now it's okay, right?
Yes, sir.
Yes, sir. It's okay.
So your temperature is increasing from 1970 to 2090, and most of us know that this temperature is likely to increase. However, when we talk of the vertical distribution of temperature, we find that in the month of June, July, August, September, there is comparatively than other seasons, the vertical distribution of temperature or increase of temperature is comparatively not that much. It's primarily because in June, July, August, September, we have more moisture available in the free atmosphere due to the monsoonal moisture. And by virtue of that, temperature is kind of damped over this region. Whereas in other region, based on the models or ensemble, which I chose, that there is a higher rate of warming happening in the temperature and as compared to the lower rate. So there is a consistent increasing trend as we climb in all the 4 seasons. In RCP 8.5, we saw pronounced winter time warming is a projected case that winter are likely to be more warming rate. I'm saying warming rate, please be reminded whenever I'm using term, I am using a warming rate as far as the vertical distribution is concerned. So these all which we saw over the Himalayan region. And then briefly I'll touch upon here for today. Most probably to understand the warming elevation dependency, why it's happening, and why at 4,000 and 3,000 meter, as I said in my previous classes, why it is happening at that threshold, that below this threshold your atmospheric characteristics are slightly different than above that threshold. So that 3,000 meter is kind of we try to look at why it's happening, that amplified warming is happening at the above, not the below. And then we find, based on certain analysis of using mean temperature, downwelling, long wave radiation, soil moisture, total cloud fraction, so on and so forth, specific humidity. So we picked up various variables from the sources, and based on that we try to see that why the elevation dependent warming is so peculiar over the Himalayan region. And we found two very distinct reasons, that at 3,000 meter you have a lot of cloud formation is happening. Generally cloud will form, is not it? So if moisture is getting up in the free atmosphere, somewhere it has to form the cloud. So in case of Himalayan region, we find that there is a decrease of downward long wave radiation at the surface of at the observation. So what's happening, that where the cloud is forming at 3,000 meter, it's not letting the long wave radiation coming down to the surface, and that is one of the reasons that you have higher temperature. We also at the warming rates are higher at the higher elevation as compared to the lower elevation, because a lot of energy intercepted by these clouds in the above atmosphere, which is kind of increasing the warming rate more than the lower elevation warming rate. Second, another, of course, this is seen from the cloud fractions also. We saw that total cloud fraction also, we find that roughly at 3,000 meter or 3,500 meters, it is a kind of supporting, that is a count of cloud fraction is kind of percentage year is kind of playing a more distinctive role at 3,500 meters. And another important, that by virtue of this feedback mechanism, what we found that these higher Himalayas is primarily having a lot of snow cover. Of course, we have yet to comprehend on that. We have yet to see on that we have a lot of snow cover is happening there. So snow is also playing a kind of a role for providing moisture to the free atmosphere. So increased DLR at higher elevation, could be due to various coupled feedback. It's not simply what I said, like it's a radiation, moisture sensitivity is there, cloud cover is there, soil moisture is there. The pattern is clearly reflected in downwelling long wave rate. That's what I said. But beyond 3,000 meter, rate of snow melt tends to decrease with the corresponding increase of albedo. So surface albedo is increasing at the beyond 3,000 meters, and snow melt is decreasing. So they are the kind of a couple of feedback mechanism is working together. And I will stop it here for today's talk. Tomorrow I will get back to downscaling at the lower sub-basin scale from Himalaya. So I will stop here, and for next 5 minutes, I'll request the participant to ask me whatever possible. I'll answer whatever I do not know. Maybe I'll get back to you later, or I'll myself work on that. So I will open this for question and answer. Is that okay?
Yes, sir.
So,
Hello.
yeah, please ask. I'm listening.
Hello.
Yes, I'm listening, please.
Good morning, sir. I am Lala Ishwari Prasad Rai from Central Agriculture University, Parapani. Sir, just I want to know what are the chemistry behind formation of this cloud burst in high altitude region. Mostly, it happens in the state of Himachal Pradesh and Jammu Kashmir.
Cloud burst in the Himalaya, I think it's a very, you ask a question which I researched a lot. Maybe I try to define a cloud burst. Now, in particularly Himalaya, cloud burst cannot happen without these two mechanisms. What is orographic locking and convective triggering? If any of one of these processes are missing, cloud burst will not occur. So now what I say, orographic locking, there is a convective triggering occurred. So instability has occurred in the free Himalayan region, and some perturbation has gone up. If this perturbation is because of the convective available potential energy, this kept on increasing, and until unless it is not locked in orographic forces, the cloudburst will not occur. Because in cloudburst, you have to have certain amount of water in a very less amount of time, right? So if that is not happening, so both the processes are needed for cloud burst formation to occur, right? Orographic convective initiation and orographic locking. So एक cloud burst एक रिव्यू मेरा पेपर है, आप उसको थोड़ा सा पढ़ लीजिए, गूगल में आपको आसानी से मिल जाएगा क्लाउड बर्स्ट रिव्यू. उसमें ये मैंने बहुत सिंपल तरीके से एक्सप्लेन किया. थैंक यू. नेक्स्ट क्वेश्चन प्लीज.
Yes.
Happen more often. Less and no less than the government offices of India. The number of humanitarian crises is increasing, and global trends indicate that this is just going to get worse. This means that the number of children deprived of their right to education and opportunities for well-being
आवाज नहीं आ रही है.
will also grow. An earthquake destroys schools.
I have muted my sound. Somebody was talking, that's why. Please ask your question.
Actually, sir, somebody is not talking, but he is also attending some more seminar also, and that is the sound is coming.
Okay. So, do you have more question, please?
Sir, I would like to one question.
Please.
Sir, my name is Dr. Sandesh Yadav.
Yes.
And in a earlier back 1 year, sir, I visited Dehradun, sir.
Yes.
And sir, on my field survey, what I observed is that a huge deforestation is taking place over there, with constructional activities like hotels, restaurant, and other activities taking place at a much greater height, sir.
Okay.
So what sort of impact they are going to have on the mountainous climate, sir?
See, when these kind of firstly, let's understand, it will change the land use, land cover, right? Where there was a forest, now there are buildings. I'm just taking a theoretical perspective. If you cut the forest, make a building, make a road, so your surface property has changed, which is supposed to be forest. Now you have kind of a more land happening there, this concrete is there. So by virtue of that, what is happening? Your emissivity flux will change naturally with the atmospheric interaction and couple of interaction, things will change, right? If that is happening, so naturally you have more change in the regional climate will occur accordingly. If you have more concrete, definitely you have a more available diabetic heating is happening there. If you what you are talking, not only in Dehradun, even Delhi, if you see, you have a concretization everywhere, and that's why you have a lot of fog in the winter and summertime, because the surface wind is almost zero, because they are vertical towers now. So the surface wind has almost stopping, it's not letting the fog to go away. So you have urbanization problem will come. Similarly will happen at many other places. If you put a lot of forest, so maybe you have a fog in winter time, and so on and so forth. So any land use, land couple change will have this thing. I hope I could answer you in a very theoretical manner.
Yes. Thank you, sir.
We have done experiment, but it's a different scale experiment. Please, anybody else?
Good morning, sir. Am I audible?
Yes, I can listen to you.
Sir, myself Kanu Charan Panda from Banaras Hindu University. Sir, I would like to ask one question that there are so many GCMs. How to select the GCM for your study area, and further how to, after selection of GCM, how to select the predictors from the.
Okay. Which department you are in, BHU?
Sir, agricultural engineering.
Institute of Agricultural Engineering.
No, Institute of Agricultural Sciences, Department of Agricultural Engineering.
So, Dr. Panda, you see what you want to do first. Now, you have. That's what I said. We need to know I know there are plenty of GCM, plenty of RCM. It's headache to me also. Now, you suppose you are looking at the rice cultivation and what is the climate change. So most probably over the Punjab or any Bihar region, suppose. So you cannot to go to the GCM. GCM philosophy is for global climate.
Yes, sir.
You have to come take RCM, and RCM also those regional climate model which are simulated over the Indian region. Because GCM is meant for large scale global perception, global forcing to intercept, not at the Indian scale what agriculture happened over the Punjab. That's not the GCM philosophy. So basically it is something like you are running 1,000-meter marathon or 100-meter. Both are race. Both are running, both are race, marathon as well as 100-meter sprint. But now the point is, for running 100-meter, you will plan for 1,000-meter marathon, so it will not give you the fetching results. So you have to go for RCM, take those data, and what you want to see for crop interaction, most probably in agriculture paper, which we have seen in the climate dynamics and climate change, mostly you talk of precipitation, moisture and temperature.
Sir, my issue is that we are developing a new methodology. So we are trying to apply it for whole India, several different Indian regions. So we are using the GCMs.
Now, what you are trying to do? That's what I'm telling you. You said you are trying, but what you are trying, you didn't say.
We are trying to modify a pre-existing Mars multivariate adaptive regression spline-based methodology. We are developing a new methodology. It is
then don't go to technical model. You are doing a spline method is a statistical method.
Yes, we are modifying that using some R codes.
Good, modify that. I am no one to tell you yes or no. I am telling you your method which you are trying is a statistical method which you are doing.
Yes, sir.
I think it's a multivariate or whatever you are trying. These are dynamical model. You have to understand now the difference between statistical model and dynamical model. Dynamical model means each time scale, whatever you do, you have a variable. Maybe 1 second, 10 second, 1 hour, 10 hour, 1 year. But in statistical, you don't have anything happening between two time steps. Because in statistical method, you don't use time scale. There is nowhere time.
Yes, sir.
Whereas in these models, you have a deva u, deva t, t star.
Okay, sir. Okay.
Thank you, Pandaji.
Thank you.
Is it okay then? Shall I call it off for today, Dr. Avasti or Dr. Nema?
Yes, sir. Thank you very much, sir. Your lectures were very informative. You have wonderfully presented the session. And thank you, participants, also for attending this session. We are closing this session for now, and we will meet tomorrow also in the same time.
Same time. Thank you very much. Have a good day.
Thank you. Thank you.
Avasti ji, shall I ask a question?
Sir, Avasti sir is not present. Actually, he is attending the second meeting.
No. What I'm asking you that is there any sort of a feedback link you are going to send to us, all of us?
Yes, sir. Post session, we are going to send the feedback link.
Okay. So you will send in the chat box, sir?
No, sir. After this session, once the session is completed, all 3 sessions, then we will send the feedback link.
Okay. Thank you.
Thank you very much.